Increasing transformer voltage to 480 volts can provide several benefits. Firstly, improved motor efficiency occurs. Higher voltage reduces the current flowing through the motor, resulting in reduced copper losses, which are also known as I²R losses. This reduced current lowers the temperature of the motor, increasing its efficiency and extending its lifespan. Secondly, it reduces energy consumption. Operating motors at lower temperatures requires less energy to maintain their operation. The reduced copper losses also contribute to lower energy consumption. Thirdly, it increases power factor. Higher voltage improves the power factor of induction motors, reducing reactive power consumption. This can result in lower energy bills and improved grid stability. Fourthly, it reduces maintenance costs. Cooler running motors experience less insulation breakdown and bearing failure, leading to reduced maintenance costs. Extended motor lifespan also reduces replacement expenses. Fifthly, it increases capacity. Increasing voltage can allow for higher load demands without overloading the motors. To calculate the savings from increasing transformer voltage to 480 volts, use the following steps. Firstly, calculate the motor efficiency improvement. The change in efficiency equals 1 minus the quantity of the new current squared divided by the original current squared times the quantity of 1 minus the original efficiency, where the change in efficiency is the change in motor efficiency. I is the original current. I prime is the new current at the higher voltage, and eta is the original motor efficiency. Secondly, calculate the energy savings. Energy savings equals the change in efficiency times the load power times the operating hours, where the energy savings is the amount of energy saved per year. Low power is the power consumption of the motor, and operating hours is the number of hours the motor operates per year. Thirdly, calculate the maintenance savings. Maintenance savings equals the quantity of the original failure rate minus the new failure rate times the motor replacement cost times the number of motors, where the original failure rate and new failure rate are the failure rates at the original and new voltage levels. Motor replacement cost is the cost to replace a motor, and number of motors is the total number of motors affected by the voltage increase. Fourthly, calculate the total savings. Total savings equals energy savings plus maintenance savings. The calculation should be performed for each motor or group of motors affected by the voltage increase. The cost of transformer modifications and potential impact on other equipment should also be considered. A detailed engineering analysis may be necessary to ensure safe and optimal operation after the voltage increase. Let's delve deeper into the specifics of each of these benefits. Examining motor efficiency. Consider that a motor's efficiency is significantly affected by the current flowing through its windings. High current leads to greater resistive losses in the copper windings, manifesting as heat. By increasing the voltage, you proportionally decrease the current required to deliver the same power. This reduction in current translates directly to reduced I²R losses, where I is the current and R is the resistance of the windings. The heat generated is reduced, which in turn lowers the motor's operating temperature. Lower operating temperatures not only improve efficiency but also extend the lifespan of the motor's insulation, bearings, and other components. Now examining reduced energy consumption. The reduction in copper losses directly impacts the overall energy consumption of the motor. Since less energy is dissipated as heat, more of the input energy is converted into useful mechanical work. This is especially beneficial for motors that operate for extended periods or under heavy loads. Furthermore, cooler running motors require less cooling, whether through internal fans or external cooling systems, which further reduces energy consumption. Also, the power factor increase results in improvements from operating motors at higher voltages. Induction motors inherently draw reactive power, which does not contribute to useful work but still burdens the electrical grid. Increasing the voltage often improves the motor's power factor, bringing it closer to unity. This means that the motor draws less reactive power and more real power, which is the power that performs the actual work. Improved power factor reduces the overall current drawn from the grid, minimizing losses in the distribution system and potentially lowering energy bills, especially in facilities where power factor penalties are enforced. Now let's investigate the reduction of maintenance costs. Cooler operating temperatures have a profound effect on motor lifespan and maintenance requirements. Excessive heat is a primary cause of insulation breakdown, bearing failure, and lubricant degradation. By reducing the motor's operating temperature, you significantly slow down these degradation processes. This leads to fewer motor failures, reduced downtime for repairs, and extended intervals between maintenance tasks such as lubrication and bearing replacement. The extended lifespan of the motor also reduces the frequency of costly motor replacement. In terms of capacity increase, increasing the voltage can effectively increase the motor's capacity without physically replacing the motor. By operating at a higher voltage, the motor can deliver more power without exceeding its current rating. This can be particularly useful in situations where the load demands have increased over time or where there is a need to accommodate higher peak loads. However, it is crucial to ensure that the motor's insulation and other components are rated for the higher voltage to avoid premature failure. Let's consider the calculations for savings. The motor efficiency improvement calculation provides a quantitative estimate of the efficiency gains achieved by increasing the voltage. The formula takes into account the original current, the new current at the higher voltage, and the original motor efficiency. The change in efficiency represents the percentage increase in efficiency due to the voltage increase. This value is then used to calculate the energy savings. The energy savings calculation estimates the amount of energy saved per year as a result of the efficiency improvement. The formula multiplies the change in efficiency by the load power and the operating hours. The load power represents the average power consumption of the motor, and the operating hours represent the number of hours the motor operates per year. The resulting energy savings value represents the amount of energy saved in kilowatt-hours per year. The maintenance savings calculation estimates the reduction in maintenance costs due to the increased voltage. The formula takes into account the original failure rate, the new failure rate, the motor replacement cost, and the number of motors affected by the voltage increase. The failure rates represent the probability of motor failure per year at the original and new voltage levels. The motor replacement cost represents the cost to replace a motor, including labor and materials. The number of motors represents the total number of motors affected by the voltage increase. The resulting maintenance savings value represents the reduction in maintenance cost per year. The total savings calculation simply adds the energy savings and the maintenance savings to arrive at the total savings per year. This value represents the overall economic benefit of increasing the transformer voltage to 480 volts. Here are some additional considerations that need to be taken into account. The calculation should be performed for each motor or group of motors affected by the voltage increase. This is because the savings will vary depending on the motor size, load, and operating conditions. It is also important to consider the cost of transformer modifications. Increasing the transformer voltage may require modifications to the transformer itself as well as to the associated switcher and protective devices. These modifications can be costly and should be factored into the overall cost-benefit analysis. The potential impact on other equipment also needs to be assessed. Increasing the voltage may affect the performance of other equipment connected to the same electrical system, such as lighting, heating, and control systems. It is important to ensure that all equipment is compatible with the higher voltage to avoid damage or malfunction. A detailed engineering analysis is necessary to ensure safe and optimal operation after the voltage increase. This analysis should include a review of the electrical system, load calculations, and protective device coordination. It is also important to consult with qualified electrical engineers and contractors to ensure that the voltage increase is implemented safely and in accordance with all applicable codes and standards. Let's elaborate further on the formula for motor efficiency improvement. The core concept behind this formula lies in quantifying the reduction in losses due to the decrease in current. The formula, delta efficiency equals 1 minus the quantity of I squared over I prime squared times the quantity of 1 minus eta, directly correlates the change in efficiency to the square of the current ratio. The squared relationship emphasizes the significant impact of current reduction on efficiency. A small decrease in current can lead to a disproportionately larger increase in efficiency. The original current, I, represents the current drawn by the motor at the original voltage. This value is typically obtained from the motor's nameplate data or measured using an ammeter. The new current at the higher voltage, I prime, is the calculated current the motor will draw after the voltage is increased. This can be estimated using the formula I prime equals I times V1 over V2, where V1 is the original voltage and V2 is the new voltage. The original motor efficiency, eta, represents the motor's efficiency at the original voltage. This value is also typically obtained from the motor's nameplate data. It is important to use the motor's actual efficiency rather than an assumed value for accurate results. Now let's discuss the energy savings calculation in greater detail. The energy savings calculation builds upon the motor efficiency improvement calculation to estimate the total amount of energy saved per year. The formula, energy savings equals delta efficiency times load power times operating hours, considers the efficiency improvement, the motor's power consumption, and its operating hours. The load power represents the average power consumption of the motor under typical operating conditions. This value can be estimated based on the motor's horsepower rating and its load factor. The operating hours represent the number of hours the motor operates per year. This value should be based on actual operating data wherever possible. Let's break down the maintenance savings calculation. The maintenance savings calculation quantifies the reduction in maintenance costs due to the increased voltage. The formula, maintenance savings equals the quantity of original failure rate minus new failure rate times motor replacement cost times number of motors, takes into account the change in failure rates, the cost of replacing a motor, and the number of motors affected. The original failure rate represents the probability of motor failure per year at the original voltage. This value can be estimated based on historical data or industry averages. The new failure rate represents the probability of motor failure per year at the new voltage. This value is typically lower than the original failure rate due to the reduced operating temperature and stress on the motor components. The motor replacement cost represents the cost to replace a motor, including labor and materials. This value should be based on actual replacement costs whenever possible. The number of motors represents the total number of motors affected by the voltage increase. This value is used to scale the maintenance savings to the entire population of motors. Here's additional insight into calculating failure rates. Estimating the original and new failure rates can be challenging, as these values depend on various factors such as motor age, operating conditions, and maintenance practices. Historical data from the facility or similar facilities can be used to estimate these values. Industry averages for motor failure rates can also be used as a starting point. It is important to consider that the new failure rate will likely be lower than the original failure rate due to the reduced operating temperature and stress on the motor components. The extent of the reduction will depend on the specific motor and operating conditions. A conservative approach is to assume a moderate reduction in the failure rate, while a more aggressive approach can be justified if there is strong evidence to support a larger reduction. Considering transformer modifications, increasing the transformer voltage may require modifications to the transformer itself, as well as to the associated switchgear and protective devices. The transformer modifications may include changing the transformer taps, upgrading the transformer insulation, or replacing the transformer entirely. The switchgear modifications may include upgrading the circuit breakers, fuses, and other protective devices. The costs of these modifications can be significant and should be factored into the overall cost-benefit analysis. Now let's discuss the impact on other equipment. Increasing the voltage may affect the performance of other equipment connected to the same electrical system, such as lighting, heating, and control systems. It is important to ensure that all equipment is compatible with the higher voltage to avoid damage or malfunction. Lighting systems may require adjustments to the ballast or replacement of the lamps. Heating systems may require adjustments to the heating elements or replacement of the controls. Control systems may require adjustments to the voltage settings or replacement of the components. Let's discuss performing a detailed engineering analysis. A detailed engineering analysis is essential to ensure safe and optimal operation after the voltage increase. This analysis should include a review of the electrical system, load calculations, and protective device coordination. The review of the electrical system should include an assessment of the wiring, grounding, and bonding. The load calculations should include an assessment of the motor loads, lighting loads, and other electrical loads. The protective device coordination should include an assessment of the circuit breakers, fuses, and other protective devices. It is also important to consult with qualified electrical engineers and contractors to ensure that the voltage increase is implemented safely and in accordance with all applicable codes and standards, such as the National Electrical Code, or NEC. Here's a summary of the key steps involved in increasing transformer voltage to 480 volts. Firstly, assess the existing electrical system. This includes reviewing the transformer capacity, wiring, grounding, and protective devices. Secondly, perform load calculations. This includes determining the motor loads, lighting loads, and other electrical loads. Thirdly, calculate the motor efficiency improvement. This involves using the formula discussed earlier to estimate the increase in motor efficiency due to the voltage increase. Fourthly, calculate the energy savings. This involves using the formula discussed earlier to estimate the total amount of energy saved per year. Fifthly, calculate the maintenance savings. This involves using the formula discussed earlier to estimate the reduction in maintenance costs due to the voltage increase. Sixthly, evaluate the cost of transformer modifications. This includes estimating the cost of changing the transformer taps, upgrading the transformer insulation, or replacing the transformer entirely. Seventhly, assess the impact on other equipment. This includes evaluating the compatibility of lighting, heating, and control systems with the higher voltage. Eighthly, coordinate protective devices. This includes ensuring that the circuit breakers, fuses, and other protective devices are properly coordinated to protect the electrical system. Ninthly, implement the voltage increase. This involves working with qualified electrical engineers and contractors to safely and effectively implement a voltage increase. Tenthly, monitor the results. This includes tracking the energy consumption, maintenance costs, and motor performance to verify the savings and ensure that the system is operating properly. In conclusion, increasing transformer voltage to 480 volts can offer several benefits, including improved motor efficiency, reduced energy consumption, increased power factor, reduced maintenance costs, and increased capacity. However, it is important to carefully consider the costs and potential impacts before implementing a voltage increase. A detailed engineering analysis is essential to ensure safe and optimal operation. Remember to consult with qualified electrical engineers and contractors to ensure that the voltage increase is implemented safely and in accordance with all applicable codes and standards.